Get there in a minute though. Gains and attenuation. We're going to look at the difference between gains and attenuation, state relationship between voltage, current, and power gains, calculate gains, inputs and output, and convert gains to dB or decibels. So what is gain? Gain is when you get more out than you put in, right? So what's attenuation? You get less out than you put in. That makes sense? What's a bell? In logs, we'll look at that, and we'll look at dB. So gains are calculated, all gains are calculated as out over in, out divided by n. Gains do not have a unit, so that's like beta, so beta is the gain, right? Understand that. If a voltage amplifier has an input of 100 millivolts and an output of 5 volts, what's the gain? I'm waiting. So an input has an input putting 100 millivolts in, we're getting 5 volts out, what's the voltage gain? Out over in. 5 divided by 0.1. So what's the voltage gain? Okay. Out over in. 5 volts out, 100 millivolts in. Huh? 50 watts. Say nothing. Gain has no unit. The gain has no unit. Y'all understand that? Gain is just the multiplier divider. So now that I know I got a gain of 50, I say, well, I measured 10 volts out. I've divided by the gain. It tells me I put 200 millivolts in. So gain is just a unit. We either divide it. If I'm trying to find out what's on the input required to get the output, I divide. If I want to find what's on the output, knowing the input, we multiply. So gain is just a unit. Fractional gains means there is a loss in the system because the output is less than the input. So what would be the gain if I'm putting 8 watts in and get 6.56 watts out? Huh? 6.56 out, 8 watts in. It's going to be less than 1. You need to cover your notes up. Out over in.
800.
What's that? 0.82. If your input is smaller than your output, if your input is greater than your output, your answer is going to be a fraction. Right? Cover your nose up now. Notice the gain has no unit. 0.82 gain. Gains do not use engineer notation. Out over in.
So 5 volts into the 100 and...
No. When you say into, it's out divided by in. So it's 100 millivolts into 5, right? You understand? Yeah. You probably knew what you said, but you said it back. Now over here, I'm getting 6.56 out. I'm putting 8 in. So fractional gains are technically referred to as attenuation. But most people just call it gains. Gains are multipliers and have no unit. If You know the gain of the input to the circuit, how can you calculate the output? So you take the input, multiply it by the gain, that'll give you the output. If you know the gain of the output, how can you calculate the input? You take the output and divide it by the gain, right? An amplifier has a gain of 23. What will be the output of the amplifier if 20 millivolts is placed on the input? I'm giving you the gain of 23. I'm telling you what I'm putting on the input, and I want to know what I should expect on the output. So what we got? So Mario's got 0.46. Anybody else got anything different? So N, right, times the gain. And the time of time. Okay? Yeah, that's all it is. But that's all you do in this. But it's still a three-term equation, right? You understand? So even if you don't remember, you can come up here and say, well, okay, I know that gain is equal to out over N. So gain is equal to out over N. So now that I've got it like that, I can put it in this little thing that y'all learn how to do back in DC, right? Where I can come through and do this, and I can say gain is equal to out over N. If I want to find N, I take out and divide it by G. If I want to find out, right, you understand, if I want to find the gain, I take the out and divide it by N. So that's the same little thing little trick that you learned in DC. And you can do that with any three expression equation. Any. And it makes it easier to solve. An amplifier has a gain of 45. What amplifier input voltage will cause 7.2 volts to be measured on the output? So here we're calculating the N. I know the gain, and I know the out. So here we would divide, right? Everybody okay? So multiplying the input with the gain by dividing the input with the gain. So this is 460 millivolts, and this right here would be 160 millivolts. The signal passes through multiple gains. The gains are multiplied together to come up with the overall gain. So the analogy I use, you're getting paid $3 an hour. And I say, I'm going to triple your salary. You're not going to add 6, right? You understand? I'm going to take 3 times 3, right? Now triple again, it's going to be times 3. So that means if I come through a bunch of amplifiers, and I'm just going to draw it like this. And this guy here has a gain of 10. This has a gain of 3. This has a gain of 4. Then what's my total gain going to be? Huh? Okay, so I'm getting $3 an hour. And my boss says I'm going to triple your salary. So am I going to add 3 to it? You multiply the gains together. Huh? Yeah, and then I triple your salary again. Now you say, well, make them $9 an hour. But so I would like to be your boss, right? You tell everybody you get these gains. Oh, I was making $3 an hour. My boss tripled my salary. Now I'm making $6 an hour. And then he tripled it again, right? They'll say, now I'm making $9 an hour. You tripled my salary twice, and I'm making $9 an hour. So gains are multiplied together. So this is what we can do. So we start off, and this is why amplifiers have multiple stages. First of all, we're trying to get impedance matching. And the more gain you have, the noisier the amplifier is, because it'll pick up all kinds of stuff. So we start off with low gain, and then we move toward the output, right? Does that make sense? So, of course, now it's hard to see because now you look at all, you open up, used to in old stereo systems, and it's still this way in power amps, because it's hard to get an IC that can handle 1,000 watts of power. So power amps is still going to have a lot of stages of bipolar transistors. So 760, I forgot a fraction. So you just multiply them together. So what would be the overall gain of a system that has the following individual gains? So we got 2 attenuations in there, 3 gains. You just multiply them all together, right? So that's the advantage of a Darlington pair. So a Darlington pair means we talked about this, we take the emitter of one transistor and feed it directly into the base of another transistor. And right now I'm just going to put a resistor right here, So let's say this guy here has a gain of a beta of 30. This guy here has a beta of 30. What would be my total beta? So we call this a Darlington pair, and you can buy these guys. I mean, you can buy them. So we would have a total gain of 900, right? You can see this a lot. In fact, even on the video I showed you that. So 24.6375. Everybody okay? Makes sense.
I know we break back that last one, so I just want to wrap the one before that. At the end, okay, so I think that the last 20 millivolts times that's that now.
Yeah, sorry.
Out on the end, we had to multiply that 20 by something.
Well, these are just total gains. Yeah. Yeah, so that's a good point. So what we're doing is we're putting 20 millivolts all the way on the left-hand side, and we're running it through 3 amplifier stages. So you don't multiply each one of them. You get the total gain of the system. You take the input, then you multiply it by the total gain of the system, and this gives your output. That make sense? Yeah, so your inputs and outputs are going to have units, but gains have no units. They're either multipliers or dividers. That's all it is. You'll run in this in gear ratios. So out over in. You got a gear on the output that's got 1,000 teeth. You got a gear on the input that's got 50 teeth. Out over in. So the torque gain would be 1,000 divided by 50. That would be the torque gain. I'm sorry, 1,000 times, out over in, 1,000 divided by 50, that would give you the torque gain. So you'll learn that all through your career when you deal with outs and ins, gears, pulleys, belts. You wonder why you shift gears in your car and stuff like that, right? I'm saying, because you're changing these gear ratios to get either more torque or less speed, or more speed and less torque. Attenuation, fractional gains creates an output that is less than the input. This is often referred to as attenuation. In power communication media, attenuation is also defined as the loss of signal strength over distance. All media has it. Everything's got attenuation, right? Everybody understand that? A communication channel consists of multiple devices as the following gains. Of course, we multiply it off. Figuring the gain. So what would our gain be here? So I would come up here and I'd take what, 247 times 567 times 0.34 times 45 times 0.67.
You forgot it. 700.
Well, it's not, what'd you say?
You forgot a 7.
Okay.
Now, just kind of go back on the situation is it's practice.
Attenuation is you get less out than you put in. Now you gotta understand, amplifiers don't create power. Amplifiers just manage the power that's already there. And that's why we call these things, what do we call these things right here? Power supply. So Alabama Power is supplying the power, right? Somehow they got some type of transducer that's converting forms to energy. But we can't create energy, all we can do is change its form. Right? You understand that? So that means my computer, I got amplifiers in here that I might be getting more out than I'm putting in on the amplifier. I might be putting 100 milliwatts in and getting 1,000 milliwatts out. But that power is being provided by a power supply. So amplifiers, all it does is monitor the power that's already there. If they created power, that means you can go out there and you can disconnect your battery, disconnect your alternator, and turn on your radio when it would work. So those devices don't create power, they manage the power that's already there from the power source. So, like we said, this requires a calculator. When we start dealing with these complex gains and attenuations, it's going to require a calculator. So, this is what I came up with. We okay? Exponents consist of two parts. We have what we call a base, and then we have what we call the exponent. An exponent indicates the number of times the base is multiplied by itself. What is represented by the number 5 raised to the 6th power? So all y'all's got a Y to X key on your calculator where you can calculate. But instead of giving the number, it's a lot more convenient to do what? To give it in this form. And what's nice about, once we got it in exponents, if your base is exactly the same, you multiply just by adding the exponents together. So it makes it a lot easier to multiply and divide. So if you divide, you subtract the exponents. But they all got to have the same base. Exponents allow very large numbers to be represented with very few digits. Most scientific calculators provide a Y to the exponent. Everybody okay? Yes or no? If the base is the same, numbers with exponents can be multiplied by adding the exponents together. So this is 3,125 times 125, and we come over here, and this would be 390,625. If I take 5 to the 5th and multiply it by 5 to the 3rd, then I can say 5 to the 8th, and it should give me the same answer. So that's one of the big advantages of exponents. It allows us to represent real large numbers. And that's why we use engineer notation. Milli, micro, kilo. So all we're doing is taking 10 raised to some power, right? But we move in groups of 3. So we can do this. We can add exponents without calculators. Now to get the final number, you've got to use a calculator. Are we okay? Same over the same number. Logarithms are numbers represented at exponents that use a constant base. We have 2 we call common logs, which is always 10 raised to some number. So that's all common logs. So if I come over my calculator, and I just use one we know, and I come up here and say 100, and then I come over here and find the oh, here we go. I'm looking for that's the natural log right there. Ah, here we go. Thank you. So if I come up here and say 100, and then I hit the log, it says 2. So 10 raised to the second power is 2. Because 10 is understood on a natural law, right? Y'all understand that? Or I'm sorry, common law. So common laws, all they are is this number raised to some power. So if I come up here and put 1,000, then the log of 1,000 is 3, which is 10 to the third. If I come up here and just make up a number, and then I hit log, then that's going to be 10 raised to the 0.3666666 power. And this calculator carries it out really, really long. Most handheld calculators only carry it out to like 10 digits. So natural logs, these basically varies with the way things vary in nature. So your ears are natural logs, the way they hear. In communication and power, the common log is used. So this is what we use all the time. When we start talking about, Cameron was talking about stereos, talking about DD on that. So. Everybody okay? A common log is 10 raised to some power. The power to which it is raised is called the bell. B-E-L, not B-E-L-L. What is the bell of 10 raised to the 5.265 power? Well, it's 5.256, right? You understand? So this is the bell right here. Everybody okay? Everybody okay what? Okay. So to convert the bell, so you notice they're usually right there together. In fact, some of them are shifted functions. We have 10 raised to some power. Right beside it is going to be your log key. Now, some calculators don't have a different key for natural log and common log, so you make sure you switch your calculator to common log. So that means if I come over here, and I just came over here and I said 5.256, and I hit that, that's going to be the opposite of, and see, so I'll come over and hit log. So log gives you the bells, and then x-rays would convert it back to the actual number. And we do this all the time, and that's why they're right together. Everybody okay so far? So somewhere on your calculator, you got 10 raised to the x power, and very close to it is the log key. Sometimes they're the same key. You hit the function key to switch between 10 to the x and then the log. So notice this is bells. That would be the actual number represented by 0.5. Oops. I messed up it wrong too. 5.256. Okay. Everybody okay? Any number can be represented as a common log if enough decimal points are used in the bells. It's just like any number can be represented using engineer notation. Any number. Y'all understand? But sooner or later, we're going to say, what do we say? We say round to 2 digits, round to 1 digit, so vice versa. As soon as you round, you're losing accuracy. But we're not shooting for perfect accuracy. We're shooting for something where I can tell if something is good or if I can tell if something's bad. So that means right now that's the number, but if I came over here and used 5.23, 5.23, sorry, clear. 5.23 and hit that. It's still close enough for me to do what? Tell if it's right or wrong. So we can round, sometimes we round the bells. Especially when they get extremely long. Everybody okay? I like it. What is the actual number for 2.4 bells? Well, I would come over here on my calculator. It's up here somewhere. And I would just say 2.4 and hit that key right there. That would be the actual number. Everybody okay? Yeah, 10 raised to the X power. So this is the bells right here. 2.4 bells, B-E-L, not B-E-L. So that's what 10 is raised to. Everybody okay? So that would be my answer. Rev to power decibels is equal to bells times 10. That's all a decibel is. So I'd come over here, and this is 2.4, that would be 24 dB. So all we do to go from bells to decibels is take the bells and multiply it times 10. So 24 dB. Now that's not a unit like volts. That's just like microamps or micro or milli, right? It's just that we're calling this dB. So this is not a unit, it's just a representing of what we're dealing with. So that would be 24 dB. But if I wanted to get it back to the number, I just take the number and move the decimal point to the what? To the right. Move it to the left, and then I would come back up and use my 10 to the X. So we always shift it one time. Either left or to the right. So engineer notation, you got to remember 3 times for milli, right? 6 times for micro. But in dB, we do it either shift it one time to the left or one time to the right. And we call it dB. And we round. So what that means is 2.4 is okay. It represents that number. But if I came over here and I had something like, I hit my key and I came up here and had something like this out there, right? I want to convert that to dB. We're either going to round it to 1 or 2 decimal points. That's what we converted to dB. So to convert this to dB, I would just come up here in my head. I don't even have to need a calculator. I just shift it to I take my decimal point and shift it to the right one time and say dB, and then we round. So what that does, it gives us the ability of having some accuracy, but it's not going to be perfect. So we're either going to round this. So this I would probably say 25 points. I might even say 25.5 dB because it rounds. Okay. So dB, what do? In our head, we don't get our calculator, but in my head, I multiply it by what? By 10. And then I round it depending on the specifications. A lot of technical data, they don't put fractions, they just round it to the nearest whole number. Because you're not shooting for perfect accuracy. I mean, I could represent any number to the decimal, exactly if I carried this thing out to an infinite number of combinations, right? It's just like 1/3. So what does 1/3 represent? It's 0.3, and sooner or later you gotta do what? You gotta stop, right? And then if I wanted to get it back into bells, I would come back in here, so I would round this, and I would say 25.5 dB. Now let's say I want to get the actual number. Well, I would shift the number to the what? I would shift it to the left, which is basically the same as divided by 10. And then I would come up and I would do that. That would give me the actual number. So all dB is a method of representing very large numbers and very small numbers with fewer dB. So it's just like we use milli, micro, nano, right? Those different things. But here we only got to remember to do what? Either shift it once to the right or shift it once to the left. So you don't have to remember kilo, mega, giga, and shift it different times. So basically it's a lot better, in my opinion. Of course you can end up with bigger numbers. How many dB would that be? Well, that would be 52.56 or 52.6 or 53, depending on how it's rounded. When gains are represented in dB, the number is usually rounded to none, 1, or 2 decimal points. So 5.25 bales is referred to as 53 dB or 52.6 dB, or it might be referred to as 52.56 dB. So you get into amplifiers, they're going to say, oh, you're going to have so many dB gain. Okay? And converting to dB allows numbers to be rounded and still maintain some degree of accuracy. But remember, as soon as you round, you've lost what? But we deal with so many tolerances and so just about everything we calculate with our math is perfect, but our components are not. So we will probably never calculate exactly what we'll measure, but we'll know what. We'll know when it's good or know when it's bad. And I've seen this in this class where you come over here and you calculate, 10 bows, and you come over here and measure 5 and you move on. And so if you don't know what it's supposed to be before you put your meter in there, then all you're doing is, so it's a good idea if you can't do the math. If you got a system out there that you can go in and make all these measurements while it's working and record them, then that would be okay. And a lot of the schematics, this is going to be there with you. So we'll look at amplifiers, how to take these values, even if they're given to you, and determine what's wrong with an amplifier. So we got a power supply that's out in one of our trainers in here, and we'll see if we can fix it. Convert the following to dB. Scientific calculators have a log key that converts numbers into bales. Make sure that common log is selected. Once the number has been converted to bales, multiply the number by 10 to convert to dB. So just take it and move it to the right one time, and then round it, depending on how accurate you want to be. The less you round, the better you're going to be, right? You understand? Or closer you're going to be, but it's basically useless. It's like in this class, I've told y'all, don't measure your resistance. So for some reason, this lab book wants you to measure all your resistance. Now in DC, it was important because you were proving on 12. So you was proving that V is equal to I times R, and they wanted to make sure that that V came up with what you calculated, and that would only be true if you measured the resistance, right? You understand? So if you say V is equal to 100 milliamps times 100 ohms, then you're going to get an approximation, right? You understand that? It's going to be close, but it's not going to be what? It's not going to be exact. A system has a power gain of 246.45, 565.34. I think this is the same thing that we looked at a while ago. No, this is a gain. This is a attenuation. Yeah. But really, it don't make any difference. You just, whether you know if they're gains or attenuations, you just multiply them together, yeah. So these are logs, so these are dBs. So 23.92, so we're taking it out to 2 decimal points here. 27.53 minus, but you notice when you take so you can tell right off the bat on your dB if it's a minus, it's attenuation. And then what can we do to calculate total gain now? No, because we've got it in exponents. I can multiply all this together, but if I've got it in dB, by George, all I have to do is just add them together. And we can do that with our calculator, right? We could do all this up here with a calculator, but that would be very complicated. Addition is pretty easy. So I can just add these together. So here would come up to be that number right there. Using dB, what we do is we just add these together. What would that come up to give us? $60.44 dB. You're looking at the slide. Then I can take this. This is rounded, so this is unrounded. So this is 1,105,444.57. Here we rounded to d decimal points. So this gives me 1,106,623.784. So it's not perfect, but it's what? It's close enough, right? Y'all understand that? So you learn over time. So AC, I think in AC they don't have you measure your resistance. It's hard to measure capacitors. Some meters have a capacitance meter on it. I've never seen one that has an inductive meter on it.
So gain is positive and
Attenuation, yeah. So you can do that. So if you take a fraction, you take the log of a fraction, it will always come up and give you a negative value. Even though rounded dB is still an accurate approximation of the actual power of what gain. So I can see a dB. So we know powers of 10, right? So I think so I look at this, I see this, I see this, I move it over 6, I said, well, that's 10 to the 6, that's pretty close to what? A million, without even picking up a calculator. And that's what's nice about dB, because we know a lot about powers of 10s. We learned about powers of 10s way back, I don't know if y'all did it in elementary school, since so long I've been here. But basically, that's all log is. All common logs is 10 raised to some power. That's all it is. So everybody's so scared of logs, but it's just another way that we can represent very large numbers. So when you get into systems, so this cable right here can have a maximum of 3 dB drop over 100 feet. Now to you that don't mean much, but I understand that. I know it's 70.7%. I know that, right? Because I understand dB. So minus 3 dB, that's what we call the cutoff point of just about every medium. So what happens with media is that y'all understand bandwidth? What is bandwidth? that's not it. The range, what did you say? The range of frequency a media can reliably pass. That's what bandwidth is. So it's not the number of people, it's how much stuff they're trying to do at any one time, right? You understand? So how much data they're trying to send. Most media has a bandwidth, especially because of inductance and capacitance. The bandwidth, technically, we have two types that we can look at. And this would be, so it'd start off having very low bandwidth, and then it comes up, then it goes off, and then it will start dropping down. And then it's 3 dB. And this is if you're looking at voltage. If you're looking at power, then 3 dB would be at 50%. If you're looking at voltage, if your voltage drops down 0.707, or we say 70.7%, your voltage drops down to 70.7%, that's the half power point. Do y'all understand why? That's the half power point. Y'all understand why? So let's take 10 volts. Okay. 10 volts times 10 amps. So let's say this is volts times 10 amps. Then what would my power be? So let's say we drop the voltage down to 7.07 volts. My current would drop down to 7.07 amps. You understand that? So power would be equal 7.07 times 7.07. Of course, we rounded. What does that come up again? Y'all understand that? So voltage and current are directly proportional to each other. If I half the voltage to a circuit, it's going to half the current to a circuit. So what does that come up again? 50. So that's exactly 1/2. So if I'm measuring a circuit and I know the maximum output and it drops down 70.7%, that means your power has dropped down what? 50%. So that 3 dB, and we'll look at that in a minute, that's 70.7%. So it's easy to measure voltage. It's hard to measure power. So what's required to measure power? Yeah, we gotta have two things, right? We always gotta measure two things. Measuring voltage, we only have to measure one thing. So if I've got a circuit, right, you understand that, and so this is the cutoff point. We call this the cutoff frequency. And this right here is the bandwidth. Because I know y'all. What's the difference between broadband? What's broadband and baseband? Y'all probably never heard of baseband before. So I'm using baseband. This is baseband. The internet is using broadband. What's the difference between baseband and broadband? When it's connected to Ethernet Wi-Fi, it's baseband. The internet uses what we call broadband. Y'all know what those are? So baseband, only one device can be on the network at any one time. But So when that device is on the network, it has the full bandwidth of the media. Broadband means you take the bandwidth of the media and you divide it into little cells. So if you had 1 megahertz, and then you had a bandwidth of, I gave you a bandwidth of 10, then there could be 10 people on the network at the same time. But they don't get the entire bandwidth. What's nice about broadband is you're almost guaranteed to get access. Baseband, the more people that's on the network, the less chance you're going to have to get on it. But right now, is my computer on the network? No, it's connected to the network, but it's not on the network. It's not trying to transmit data. So networks transmit data in what we call packets. So one packet is usually around 4,096 bytes. Then it comes off the network, right? So baseband basically you're more, but still if the more people that's on it and you're taking up these 10 slots and you want on the network, you're not going to get off the network until somebody starts transmitting, right? You understand? So even on broadband, the more people that's on the network, the less you're going to get on. So yeah. So the bandwidth is the range of frequencies a media can reliably pass, and this is set at 70.7% of the voltage, or minus 3 dB. And we'll calculate it in a minute. Any questions? All right, guys, I'll take a break. So power varies with the square of the voltage, right? To a circuit, if the circuit does not change. So it means if I double the voltage to a circuit, power delivered to the circuit will quadruple. Y'all understand why? So so power is equal to V times I. I is equal to V over R. Right? You understand that? If R is the same, if you double the voltage, your current doubles. If you go down, it varies as 1 over. So if my power drops by 1/2, if my voltage drops by 1/2, then my power is going to drop by 1/4. Y'all understand? I think I told you about my mom and her stove. Did I tell you the story? My mom gave me a call and says Ricky, called me Rick. She said, my stove won't even boil water anymore. And I went out there, and instead of getting 240 volts to her heating element, she was only getting 120 volts. So instead of getting 1,800 watts, she was getting 1,800 watts divided by 4. And it wasn't getting hot enough to even boil water. And what had happened, I went out, she has a breaker box outside, I went out there and realized that she didn't have 240 coming from the line. One of her leads had burned off her transformer. So I don't know if it got something across it or something like that. So instead of getting the 240, she was only getting what? 120. So if voltage and this is why maintaining voltage to a circuit is very, very important. So half power is considered to be the bandwidth of a system, right? So you got the maximum power, and as soon as it drops down to half power, that means that's what we call the bandwidth. It's between the 50% power plot. So if I come over here and say, what's 50%? Well, if I came over here and took the log if I come over here and took the log of 0.5, right, you understand, I took the log of that, it's a minus 3 dB. So 3 dB is the half power point, right, you understand? So as we go up, as soon as it gets up above 3 dB of maximum amplitude, and then it starts moving across, and sooner or later, and this is what the book does a pretty good job of this in chapter 10. But so bandwidth are usually, we start off with a media, and since we have some capacitors, normally it starts off pretty close to zero, and then sooner or later it'll stop coming up, and then it'll level off, and then sooner or later, due to capacitance and inductance, sooner or later it's going to come up here and it's going to start dropping down. So every media has a bandwidth. Sometimes, like a conductor works real good at, and this is hertz right here, so this is frequency. So a conductor works really good at DC, but sooner or later a conductor is going to do this, especially if you have two conductors running together. So your bandwidth might start at 0 hertz, but sooner or later it's going to start jumping across. This is why high frequency is so hard for years and years and years, and it might still be that way. The U.S. government, the military aircraft used high frequencies that were so high that no other country could figure out how they did it. Because the higher the frequencies, these ultra high frequencies are really hard to keep them from jumping all over everything. Because every two conductors that's side by side is a capacitor. And so this would be 50% power, or minus 3 dB, which would be what? That's 50% of the power. And then this right here would be at 50%, which people say minus 3 dB. So you'll see 3 dB all the time when you deal with it. So that's the 50% power point. And that would be the 50% power point. Now, if I'm measuring voltage and I want to relate it to power, then voltage varies, power varies with the square of the voltage, right? Y'all understand that? And we'll look at that anyway. So if I'm measuring voltage, 3 dB actually occurs, and we've already looked at that, at what? 70.7%, which would be up here, would still equal to 3 dB. And we'll see how we do that. So voltage at 70.7%, and we get a good idea of what's going on with the power. Y'all understand that? Yes or no? It's pretty neat. So voltage, current's hard to measure. So to measure current, we have to break the circuit. To truly measure current, we have to break the circuit and make the current flow through it. Power is hard to measure because why? Because we have to always measure two things. Voltage we can measure. We can measure with an oscilloscope, we can measure with meters, we can measure all kinds of stuff. So it's nice to be able to relate power to voltage, right? You understand? And we showed y'all that. So I have the power, I have the voltage, half the power, right? 70.70%, and it came up with 50%. Gain, signal gain through multiple stages. I'm behind here. Decibel is total gain. And like I said, a lot of times when you got dB, like 10 to the 6, I know this is going to be somewhere around a million, right? So you get a pretty good idea without picking up a calculator. This is about the half power point you just got through talking about, the power formulas, which guys, y'all need to know these. And this is what we just got through. I just got through working on this. If the voltage circuit to triple, then the power would triple. So voltage is very easy to measure. If we half the voltage, though, power's going to drop down to 25 volts. So most people say, what, you know, and this will be on test, and somebody's going to mess it. I said, if I half the voltage to a circuit, what happens to the power? Somebody in this class is going to say the power halves. And I don't know what to do about that. Quadruples, what happens to power at quadruples, right? This is a bunch of problems. Voltage varies with the square of the power. The original 10 volts, 100 watts. The voltage will triple, right? Of what voltage we call the power to half, 0.707. We've already talked about that, right? We can change the division problem into a multiplication problem by taking the reciprocal of that. I don't know why I've got that in there. The half power point will always equal to a maximum voltage of 0.7, maximum voltage times 0.707. So understand that now, right? Everybody okay there? Fractions can be expressed as percentage, so if the voltage drops down to 70.7% of its maximum value, the power decreases by 50% of its maximum. A half power point is usually considered to be the maximum loss allowed by a meter. Everybody okay there? When they calculate the bandwidth of a stereo system, they say we have a bandwidth of between here and here, it's going to be at the half power point, right? So this is the formula. Voltage is easy to measure, power is not. Find the power gain or attenuation in dB. We're dealing with power. It's power out divided by power in, right? Take the log and multiply it by 10. Everybody understand that? So this is the way they give it. So basically you have to do it backwards. This is the formula, but you have to do it backwards. So what would I do first? I take power out. I divide it by what? Power in. Then I would take the log of that, and then I would multiply it by 10. That'd be step 2. And then I multiply it by 10. So a lot of our math formulas, we have, in our calculators, we have to enter them backwards. So one, you take the power out, power in. Then you hit the log key, and then you multiply it by 10, and that gives you dB. So most of the time, multiplying by 10, you just got to shift the decimal point to the right one spot. And round. On most calculators, this will have to be entered backwards. Power out divided by power in. Then the common log, and then multiply that by 10 either in your head or with your calculator. So that's the way they'll give it in. That's the way they'll give it in textbooks. Are we okay? So since power varies with the square of the power varies with the square of the power varies with the square of the voltage. This is the formula. So I can calculate power gain by using voltage. So I'm taking V out over V in. I take the log, and instead of multiplying it by 10, I multiply it by 20. And that compensates for the square, right? And this would be the same for current too. The current's hard to measure. This is the formula we use most often because we can measure voltage really without getting the problem. So I can measure current in over current out and use 20 log current gain. Or if I can measure power out and power in, I would multiply it by 10. But what that multiplying by 20 does, it automatically compensates for power varies with the square of the voltage. Now this formula should be, hopefully it's in the textbook, I don't know. I know it's on the formula sheet. The voltage source equals 100 volts, and the voltage at the load equals 95 volts. What is the loss in the conductor? So that would be what? 95 out of 100 in would be 0.95. We take the log of that. That would give us 0.22. We multiply that by 20. That would be 0.4 dB. The voltage on the input of a conductor measures 5 volts. The voltage on the output measures 3 volts. What is the dB loss of the conductor? So out over in, 3 over 5. You take the log of that. Then you do what? Multiply it times 20. because we want to make it relative to power. Everybody understand that? Yes or no? Mario's going like this.
Yeah, using software, they use that.
Yeah, because you're measuring voltage. But it's relative to power, right? You understand? So 20 dB, V out over V in, 20 dB, if the load is the same, then that would, you could take the same thing and it would give you the power, right? So basically you're getting the power gain by measuring what? Measuring voltage. In dB. So that's why we multiply it by 20, because power varies with the square of the voltage. And 10 to the first, or 10 squared. So you square it, right? You understand that? Anybody understand that? Yeah. Yes or no? 100, but that's the square. So that's what we're doing. We're taking 10 to the first, and then we're squaring 10 to the first, which would be 10 to the second, right? You understand that? Because power varies with the square of the voltage. Yeah. Because power varies. So what we're doing with this formula is we're getting an idea of what's going on with the power of the amplifier. So if I measure an input of 5 volts and an output of 20 volts, I want to say, okay, what is the power gain of the amplifier? Voltage gain is okay, but we want to know how much power gain an amplifier gives us, because the power is work, right? You understand that? So I would take 5 out, I'd divide it by 10, I would take the log of that, and I'd multiply it by 20. And that would be the power gain we get out of the amplifier. And a lot of people want to ignore that. A lot of people, think that voltage, but power is equal to voltage times current, right? And power is work. So what we're interested in, and the power company don't charge you for voltage, and the power company don't charge you for current, and the power company don't call themselves the voltage company or the current company. They call themselves the power company. They're selling what? Power. Power is work. So you're paying for the amount of work you're using. You're not paying for the amount of current you're using. You're not talking about the amount of voltage. You don't use voltage anyway because it's just push, right? We're paying for the amount of work. So that means I get a 4.4 dB power gain out of this circuit, even though we use voltage. And why do we need to know that? Because like I said, voltage is very easy to do what? It's very easy to measure. I can measure with an oscilloscope. I can measure with a meter. I can't measure current easily, right? Because what do we have to actually measure current, we have to break the circuit, right? I can't measure power directly. Power meters are not cheap. And you still have to break the circuit. You either got to measure AC, we can get a pretty good idea of what the current is by the strength of the magnetic field. So with AC, we have the ability to buy what we call clamp-on ammeters. Have you ever seen a clamp-on ammeter? Well, is it measuring current? No. It's measuring the strength of the magnetic field being created by the current. So you're not actually physically measuring the current. And you can't put it across 2 wires, because as soon as you put it across 2 wires, they cancel each other out. And you can loop them, by the way. If it's AC and your meter don't measure and you got enough slack, you can loop them. You can make a current for them. So if you loop it twice, then your meter, if it measures 500 milliamps, it'll measure 1 amp. And you just have to divide it by how many times you loop it. I learned that trick from I said, my clamp-on ammeter, I'd like a more accurate measure. He said, well, just loop the wire, Rich, and I'll loop. I said, man, that was so cool. And then it makes sense, because it's basically a transformer.
I had put the around the wires, and it wasn't measuring all that. That's too low.
Well, the problem is you're measuring the current in the neutral is always flowing opposite of the current in the hot. So this is doing this way, this is doing this way, and it's always canceling it out. So if you're going to measure a clamp-on ammeter, you only want to put 1 wire through it. Or we do it every once in a while to measure the differential. So, by the way, that's the way a ground fault interrupter works. It measures the differential between, it's measuring the differential between what we call the hot and the neutral. Those two currents should always what? Should always match. If they don't match, that means that other current is going somewhere between you and ground, right? You understand? If you get across the hot and the neutral on a power plug, the ground fault interrupter is not going to do anything. It considers you to be a light bulb. But if you get between the hot and neutral, the hot and ground, then it'll trip. Because now the current flow going on the neutral and the hot don't match. So that's all a ground fault interrupter is. It's just a current transformer. That's all it is.
I got a ground fault outlet out there. It just got rid of the
Yeah, within 8 feet. I think if they hadn't changed the rule, if it's within 8 feet of a water source, you're supposed to have a ground fault. Yeah. Mine don't either. I should do. So if I take 7.7, 20 log, 7.7, it's going to come up and give me minus 3 dB. If I take 10 log, 0.5, it's going to give me a minus 3 dB. Y'all understand that? So that's why the 20 log works. Y'all see what I'm talking about? Yes or no? Yeah. So if I come over here and I do these logs, and I take 0.707, and then I take the log of that, and then I multiply that by 20, I get minus 3 dB, which is voltage, right? You understand? If I take 0.5, and I take the log of that, and multiply that by 10, so this is power, I get minus 3 dB. So it's minus 3 dB on the voltage, which minus 3 dB is power, right? You understand what I'm saying? Yes or no? So a 0.5, if I'm measuring power, then 0.5 is equal to minus 3 dB. That's half. If I'm doing voltage, 0.7, I take the log of that and multiply it by 20, it gives me a minus 3 dB, it gives me a minus 3 dB power gain. So what we're saying is this formula right here gives me an idea of the power gain I've got in a circuit measuring voltage. I don't have to measure two different things. Y'all understand? But the only thing we got to know is the maximum voltage I get out. And when it drops down to minus 3 dB, which is 70.7% voltage, then that's what we call the bandwidth. Because if the voltage drops down 70.7%, the power drops down 50. The power has dropped down 50%. So usually at a maximum communication channel, 3 dB is the maximum you can have in a run. If you get more than 3 dB, then you're going to have to run it through some type of amplifier or something like that. So how many amplifiers does your phone system run through on your way to your house? Through a lot. How many amplifiers does the cable run through? But they're all matched, right? The impedance matched. So minus 3 dB. Is that power or voltage? That's power. It's just that we can calculate the power by using 20 log instead of 10 log. V out or V in. We don't look, dBm, this is all, dBm, you'll see this every once in a while, this is relative to a standard of 1 milliwatt. So you'll see that. Huh? Yeah, milliwatts. Yeah. And you'll see this every once in a while, but this is just relative to 1 milliwatt. So questions on dB? So what is decibel? What is dB?
No.
It's a way of representing large and small numbers with fewer digits. Except the way you do it is constant. So it's kind of like milli, micro, nano, but on those you got to remember how many digits to shift, right? You understand? Here you're always going to shift how many what? One. So when you go to dB, you shift it to the right one time and round it. To go to bales, you just shift it to the left one time and don't round it. Yeah. So yeah, with dB, we could represent any number. It's just like your calculator. So your calculator can represent any numbers, but sooner or later, even your calculator is going to give up, right? Yeah, this Windows calculator, it's amazing. That's like I don't know how many Windows it shipped in engineer notation. You see, it still hadn't shifted in engineer notation. But is that a perfect number? No, it's not. The calculator, even your calculator is going to run. Most handheld calculators display 10 digits. Calculates 13, displays 10. So it calculates 13, so it'll be more accurate when it rings. And then once you exceed that 10 digits, it automatically shifts into scientific notation. Okay? And then as soon as it does that, it's definitely rounded. So, is this the exact number? Probably not. So once it calculated the maximum number of digits it could do, then it's going to shift it, then it's going to shift it, it's going to start rounding. Right? Yeah, so this calculator calculates a lot of digits. It's a really good calculator. But it's a heck of a lot more accurate than you need. Okay, what time is it? Got a couple things I want to show y'all. Oh dang. So we looked at saturated switches. Everybody okay with those? Yes, no? Even if you could do the math. So we got what's the three regions we can operate a transistor in? A transistor in.